Logarithmic functions. First off, let's start with this example. Find the inverse of f of x equals 2 to the x. Now, before we can do that, we have to type in 2 to the x to make sure it passes the horizontal line test. And the horizontal line test is if you draw a horizontal line anywhere through the graph, if it goes through it only once, then it does have an inverse. This one does pass the horizontal line test. Let's talk about this graph for a second or two. Now this is how it looks. This point is 0, 1. We know that the domain from left to right is negative infinity to positive infinity. We know the range gets closer to 0, but it never gets there. So it's parentheses 0, and it goes up forever to infinity. So it does have an inverse. That means we're going to replace f of x with the y. We're going to interchange the x and the y's. And we're going to solve for y. Interesting. What does y equal? Y is the exponent. So what is the answer? Well, we're going to say it like this for now. Y is the exponent on 2. That yields x. Whew, that's a lot to say. But that's what it is. It's the exponent on 2 that yields x. You know what we're going to use to write that as shorthand? We're going to use logarithms. That's where they come from. A shortcut way to write this is that y equals log. If I say the word log, that just means logarithm, base 2 of x. Now this 2 is a small 2, it's a subscript, it's below the log x. The log x are on the same line, 2 is below. So all this is saying is that the logarithm is nothing but an exponent. That's what that is saying right there. Logs are nothing but exponents. Now this 2 is called the base. Therefore, this 2 is also called the base. Now, in general terms, this is our definition. And it is by far the most important thing that you gotta know. The number one most important thing. And here's how you do it. Or here's how you think about it. We have y equals log base a of x. That's how I say it. Log base a of x. Now that's the exact same thing as this. Now when we do this, what we're about to do with the definition, we're always going to start with the base. So the base is a. Logarithms are exponents. So this logarithm equals y, which must mean that y is the exponent on the base a. And then that equals what we haven't used yet, which is x. That is not an x. Do you see that? You see what I just did? That was not an x. This is an x. So once again, a is the base. It's the base of the log, and it's also the base of the exponent. Logs equal exponents. So y is nothing but an exponent. Therefore, y is the exponent on the base a. And the next is what's left over. Some books call it the output, but whatever you want to call it. Now here's another way to think about this. So let me erase all this, just so you can see that's a little bit easier to relate to. I erased the next. I shouldn't have. I'll put it back in there. Sometimes this eraser doesn't want to work the way I want it to. Okay. We'll put that back in there. Watch this. If you have an exponential form, you can always do this. Well, let me write it like this. If you want it in exponential form, watch this. I don't want to look at that right now. Watch this. Ready? Start with the base. You go counterclockwise. A to the y equals x. See that? Counterclockwise. Start with the base. A to the y equals x. That's how you can get that. Keep that in mind. Now the next thing that you need to know, sometimes you have logarithms that don't have a base attached to them. This one is called the common log because it's used most commonly, and plus our number system is based on the number 10. So if you see a log without a base, it's always understood to be base 10. Now if you see ln, that's shorthand for natural log. Now it's the same as log, but the base is e, because natural log is related to the natural number, and e is the natural number. So that's the same as log base e of x. It is not this. That's something totally different. ln will not have an e if you're looking for its base. It will not have an e written. The base is already understood to be written within the log form. So keep that in mind. And another thing to keep in mind is log and ln are on your calculator. If you look above the log key, you'll see 10. If you look above the ln, you'll see e. That's kind of another way to remember what the bases are. So now what we're going to do, we are going to graph log base 10, and actually it will represent most logs no matter what the base is. So let's type in log of x. Error. Anytime I get an error, hit go to. I didn't type in my x. That always hurts. Alright. Now you see this. Now what this looks like, it looks like this. Now remember, this is the inverse of this shape. Is 0, 1 is a point, and if you interchange that, that means that 1, 0 is a point, which it is. And then if the domain is negative infinity to infinity, and the range is 0 to infinity, those are going to be interchanged. I'm going to write those down, and then we're going to look at them from the graph. Domain, how far left does it go? Well, it gets closer and closer to 0, but never gets there. How far right does it go? It goes forever. Now the range, how far down does it go? It definitely goes forever. And how far up does it go? Well, this keeps on going up at a slight angle, but it does go up. It goes up forever and ever. It never stops. And something else about this, depending on your class, this has a vertical asymptote. It's the x-axis, or in other words, x equals 0. So, with that, in summary, the domain is from 0 to infinity. 0 and negative numbers are not included in the domain. That's a big deal. Range is negative infinity to positive infinity. It does have vertical asymptote from at x equals 0, and the point 1, 0 is on the graph. So now let's look at some examples involving the definition. Well, but before we do that, let's consider something that you may see that involves transformations. So I'm going to erase this. Now I'm just thinking about what do we want to use. I probably should let that graph up there, but that's okay. Let's look at this. We have y equals negative log x plus 3 plus 4. Now remember, this is the basic shape of the logarithm graph. Remember, the vertical asymptote was x equals 0. So if you look at this, that minus sign, if you remember how things work, it changes all these y values from a positive to a negative. Well, that's over the x-axis. It reflects it over the x-axis. And hopefully you recall that plus 3 is going to move it to the left 3. I want to use that minus sign, even though it's kind of a short way to think of it. But you always use the opposite sign when it's inside parentheses with the x. And then the plus 4 is attached to the y, so it moves all those up 4. And something else. See this vertical asymptote? For the regular graph, it's x equals 0. For this one, guess what it's going to be? This x plus 3, this shift left 3, is going to shift the vertical asymptote left 3 also. So instead of being x equals 0, it's going to be x equals negative 3. So let's just look at the graph. So let's type in negative log x plus 3 plus 4. Let's see if this one has been flipped upside down, moved left 3, and then up 4. Upside down, left 3, up 4. Let's see if negative 3, comma 4 is a point. Negative 3. Well, no, it's not, because it's an asymptote. Oh, see, you gotta watch my mistakes, my thought process. See this point right here? This point was 1, comma 0. So if I shift it to the left 3, that means it's going to be negative 2, and then up 4 is positive 4. So what if I hit negative 2? Positive 4, and yeah, that makes sense. And then we're saying that the vertical asymptote is x equals negative 3. What that means is, as I get closer and closer to negative 3, well, first off, negative 3 doesn't exist. But if I try negative 2.9, I get some value, negative 2. I wish I could type. Negative 2.9. That's not 99. I still get a value, negative 2.99999. I still get a value. So I can get close as I want to negative 3. I just can't use negative 3. Now your calculator is lying right here. It couldn't do that negative 2.9 as many times as I did. It rounded it off. So watch out. Negative 3 does not exist. So you may get a false error if you use too many 9s. Negative 3 does not exist. Look at your table just to confirm error. So depending on your class, this may be important, it may not be important. Now, once again, the most important thing is the definition, so we're going to do several examples using the definition. Once again, the definition states this: the log base a of x equals y if and only if, start with the base is a, logs are exponents. Since log equals y, that means y is an exponent, and then equals what's left over, which is the x. So we have everything we need to do these examples. So we're going to convert these to log form. What that means is we need to write down the word log, and then we always start with the base. What's the base of the exponent? It's 6. So that's going to be the base of our log. What do logs equal? They equal exponents. What's the exponent up here? It's x. So that means that the log equals x. And the number we haven't used yet is 216, and that goes right there in the empty spot. And that's it. Next one. Log. What's the base? It's a. What do logs equal? Exponents. What's the exponent? B. And what's left over is C. Once again, if you need to check it, counterclockwise, a to the b equals c. And this last one, start with the log. What's the base? E. What do logs equal? Exponents. What's the exponent? 2. What's left over? It goes there. E to the second equals v. Now it is true that we already know what log base e is. Log base e is the same as natural log, so we can actually write it as natural log. Now all of this is ln, and then we write down everything else. Natural log of v equals 2. That's such a big deal. That's why I've labeled these 1, 2, and 3. These are the most important things for now. Now let's go the other direction. Convert to exponential form. That means we won't have a log in our final answer. So let's start with the 4, because that's the base. Logs are exponents. Log equals 2, so 2 is an exponent, and that equals what's left over, which is the x. So 4 to the 2 equals x. Now this one, you don't see a base. If you don't see a base, it's understood to be 10. So that means that's the same as 10 to what power? to the third, because that's what the log equals, and that's an exponent, equals what's left over, which is ex. See this ln? If you need to, write it as log base e. Don't do this. That is something completely different than what this is. That x is not an exponent. The e is a subscript. So start with the base, e, logs equal exponent. The exponent is -3. That equals what's left over, which is ex. Once again, counterclockwise. Now, since we do have a couple log keys in our calculator, we're going to use that to find some of these values. Log base 10 is the same as log. So I just type in log 7. Base 10s and base e's I can do all day long on my calculator. So this one, if I round off, is approximately 0.8451. Log base 10 of 1,000, that's going to be 3 when we type it in, because when you type in log, the 10 is understood. So it needs 1,000. Log of 1,000, which is 3. Natural log of 8. Type that in, because we have an ln key. Notice ln. So I want make sure you use the ln, not the log. You'll get a different answer if you don't. We get approximately 2.079. ln of e to the third power. Now when I type this one in, let's just bring up this e over here. We got two of them. We got one above the ln and one above the division. I'm going to bring up the one above the division to the third. It has fewer parentheses. The answer is going to be 3. And I'll explain that to you later on. Now it's the log of -1. Hopefully you were listening. You know that you can't do this. No solution, no answer, does not exist. No real answer solution, however you want to think about it. Because it's outside the domain. Remember, any negative number you want to use, you're going to get the same answer. In fact, if I take the log of 0, I get an error message. Can't do it. It's outside the domain. Be careful with that. Now we have some more properties. In fact, we actually only have one main property to look at. It's this one right here. This is going to be number 4. Here's where it comes from. Let's say that we have log base a of a to the x. Let's say we don't know what that equals, so we'll call it a question mark. If I were to convert that to exponential form, I would start with the base, which is a, and then the question mark equals a log, so that's going to be our exponent, and that equals what we haven't used yet, which is a to the x. For these two bases to be the same, or since these two bases are the same, and the two sides are the same, that can only be true if this question mark equals an x, which means that the question mark equals x, which means this property is valid. Which means, if you want to think about the easiest way to think of it, you may want to think this. The base of the log and the base of the exponent are the same, therefore they like cancel out, and the base of the base of the log cancels out. That means the log cancels with it because they're attached, which only leaves the x. That's an easy way to think about it. The bases cancel. It leaves the x. Same thing here. This natural log of e to the x is the exact same thing as this, because natural log of e to the x is the same as log base e of e to the x. Those are the same, so they like cancel. It just leaves x. Same thing here. These cancel because of the same base. It leaves x. This ln is log base e. It cancels with the base of this base e, and it leaves x. Simple enough. Same bases. Now this one, I'm not going to think too much about it because I have a calculator. If I type in log of 1, you get 0. Type in natural log of 1, you get 0. And the reason why it is because you got to think about it. What are logs? They're exponents on the base that gives us, in this case, the 1. So what's the exponent such that when you raise some number to that exponent, your answer is always 1? Well, that exponent is not 1, but 0. Anything 0 power is 1. So this is like a backwards question of what you may be thinking. Since it's asking for the log, it wants the exponent on the base that equals 1. That exponent is always 0, no matter the base. And then these down here are very similar to this, which states if a to the y or a to the x equals a to the y, that's only true if x equals y. If you think about it, it has to be true. Bases are the same, the sides are the same. That must mean the exponents have to be the same. That's true for logs. Logs are the same, the bases are the same. That must mean that these x's and y's have to be the same for both sides to be equal. Same thing here, just different log. Now this third one down here, if the logs are the same and the x's are the same, then the bases have to be the same for both sides to be equal. If you take a look at those, they actually make some sense, or they're easily deciphered. So you have 4 things that you have to know, no matter what. Definition, which basically says that logs are exponents. Common and natural log are all on your calculator. You gotta know those, but use your calculator to help you out. And then, if the log of the base of the log and the base of the exponent are the same, it always equals the exponent. And before I do this one, just to give you a little heads up on how easy these can be. If you have like log base 3, 3 to 7, see these 3's? They're the same. Base of the log, base of the exponent are the same. It always equals the exponent in that case because they like cancel out. In fact, I'm going to do this one because it's a little bit easier than the first one. So natural log of e to the negative x, if you need to, that's the same as log base e of e to the negative x, which means those cancel out and it leaves the exponent. But the more of these that you see, the more that you're going to recognize that ln is understood to be log base c, which means those cancel out and it leaves the exponent. So let's do the easy ones first, which I did. Now this log of base 1/3 of 9 is not as easy as the other ones. This one requires some algebra skills. So what that means is I need this 9 to become 1/3 raised to some power. So here I go. One thing I know about 9 is it's the same as 3 squared. Something else that I know, I can take 3 squared and flip it over and make it a negative exponent. And then something else that I know, I can take that negative 2 and I can move it outside the parentheses. It doesn't change anything. Since I have same bases, it must mean that it equals the exponent, which is negative 2. Now if you're wondering what exponent rule I use go from 3 squared to 1/3 of negative 2, is the flipping exponent rule. Flipping base rule, I mean. A to the negative n is the same as 1/a to the n, positive n. What that's saying is, if you want to flip the base over, you can, but you only do that if you change the sign of the exponent. So keeping that in mind, I can now do this one. I need to have that e as a regular size e, so to do that I can flip this base over, which means the exponent changes to a negative 3. Since the bases are the same, that equals the exponent, which is negative 3. Now to do this last one, natural log of square root of e, I got to use this property which says the nth root of a to the m, which can also be written like this. I can move the m to the outside. But either way, it equals a to the m over n power. It's a fractional exponent. This n is called the index. And it's one that moves to be your denominator. So, index equals denominator. That's how you think of it, but the index moves. So keep that in mind. When you see the natural log of square root of e, the e does have an exponent, which is a 1. If you see a square root, but you don't see a number on the outside, it's not a 1. It's a square root. When you hear the word square, what number comes to mind? 2. So this can be written as natural log of e to the 1/2. Remember, the 2, the number on the outside, moves underneath. And now, since ln is the same as log base c, and the base of the exponent is the same as e, since we have the same bases, that means that it equals the exponent. And now, let's solve some equations. This first one's really easy. You know why? We're going to solve for x. This one's easy because the base of the log and the base of the exponent are the same, and they like cancel out, and it leaves the 3, and we're done. That's simple enough. Now look at this one. Both of these have the same log base 2, so they like cancel out in a certain sense. They really don't, but we can say they do. That means we're left with x equals 14. That's simple enough, isn't it? Look at this one, natural log of e to the x. Natural log, same as log base e, which cancels with that e, and it leaves x, and then the right side stays, so x equals 19. Those are all pretty simple. Now let's do the last three. These aren't as easy, but they're not that bad. We have log base 2 of x equals 6. Now the base is 2. Now this is in log form, so what I'm going to do, I'm going to convert it to exponential form. Exponential equation. So start with the base, which is 2. Logs equal exponents. The exponent is 6, because that's what the log equals. And that equals x, because that's what's left over. And then we find what 2 to the 6 is, and that's going to be 64. And we're done. Now, something to keep in mind, always check your answer. If it's a log of x, you can't take the log of a negative number. So if you were to take the 64 and throw it in for x, later on you'll see that we can do that because it's a positive number. So just be aware. Oh, we got a few more examples. So this next one, it's in log form. I want to convert it to exponential form. To do that, I need a base. If you don't see a base on the log, it's always 10. So now we can convert it to log form. Start the base, 10. What's the exponent? 2 equals, what's left over? X minus 1. And don't forget the counterclockwise thing. Don't forget that. 10 squared is 100. Add 1 to both sides to solve for x. We get x equals 101. That's the answer. Let's do this one. Before I do this one, I'm going to rewrite it as log base e of 2x equals 3. So start the base e. Logs equal exponents, so the exponent is 3. E to the 3 equals 2x. Now if I divide both sides by 2, I have my answer. X equals e cubed over 2. Now, that's a funny looking e. If I want to get an approximation, I can take out my calculator and type in e to the third and then divide that by 2. We get some value, approximately 10.04, something like that. You also could have done this. I think the division one may be a little bit better. I don't know if it really matters though. It's a preference thing. Alright, we got 2 more. It's in log form still. So start with the base, x. Exponent is 3 because that's what the log equals. Equals 125. Now I need to get x by itself. So how do I solve this? I'm going to take the cube root. Remember, a radical kills an exponent. And it leaves the x. What's the cube root of 125? If you don't know how to use your calculator, your math key has a cube root. But I'm going to show you something. You can also do it this way. You hit 3 math and then 4. Well, nope, wrong one. 3 math 5. So that 3 takes the place of that x. So the cube root of 125 is 5. Now let's do this one. This one isn't near as much fun. 2 raised to log base 3 of x equals 16. Now the first thing you need to recognize is this is in exponential form. I really can't use log form yet because I don't have enough information yet. So what I'm going to do is I'm going to rewrite it to where the both in terms of base 2. So 16 is the same as 2 to the what power? If you think about it, 2 times 2 is 4, times 2 is 8, times 2 is 16. So it took 4 2's to get to 16. See that? Since the bases are the same, that means that exponents have to be the same for both sides to be equal as they are. So that means I now have log base 3 of x equals 4. It's like these 2's cancel out in a certain sense. Now that it's in log form, I can rewrite it in exponential form. Start the base. Logs are exponents. Exponent is 4 then, equals what's left over, which is ex. And 3 to the 4th is 3 times 3 times 3 times 3, which is 81. And we are done, I do believe. Yes, we are.